So just quickly, one comment, because it's actually something that deserves a whole class, but I actually killed it in this course, and we're not going to cover that much, but because a few people asked me about it. Where is it? Who asked me about it? Well, somebody asked me about it. So in some sense, we introduce a probabilistic setting, and we introduce a framework that can account for their certainty, but then we pretty much always concentrate on learning just a function. Okay, and probability somewhat disappears. When we regularize, when we talk about overfitting, we do have probability in mind, or rather the probabilistic model, the idea that we can have just a sample of data coming from some distribution, but we don't really handle probability that much. We handle functions, we handle vectors, we mostly boil it down to linear algebra or function-like objects. This is my summary of what you could do if you don't do what I explained here. It's a bit of a joke, if you want. But the story is basically that you could take a kind of a different route where you talk only about probabilities, where you basically say, I'm going to define likelihoods, noise models of the data, and then I'm going to put priors on the objects I want to define, and then I'm going to try to write down some posterior probability on the parameters. In the simplest case, where you take just a regression model with Gaussian noise, and you put a Gaussian prior on the coefficients of your linear function, this is how the story goes. So what we've been doing so far is looking at this problem where we minimize something like this, where we have a loss term and the regularization term. Basically, you can take another point of view, which algorithmically turn out to be equivalent, where you say, no, actually, rather than take the minimum of this function, I want to take the maximum, yes, the maximum of e to the minus this exponent, all right? Of course, up to now, I did nothing. Instead of a minimum of something, I took the maximum of e to the minus that. The value of w that solves either one of these problems is going to be exactly the same. The truth is that in doing this, I'm actually able to look at this quantity as the product of two Gaussian. This Gaussian, sorry, there is a square missing. Okay. Which turns out to be the Gaussian that describes the likelihood of the data under Gaussian noise model. And this Gaussian, e to the minus this, would turn out to be the assumption that the w, the coefficient w's, are distributed according to a Gaussian. Okay? And of course, you can say, well, what if they're not distributed according to a Gaussian, but they're distributed according to some other distribution, for example, a Laplacian and so on? Well, you just have to replace this term here. So if this is a probability, what are we doing here? We're just taking the maximum of this probability. Okay? And so up to now, we did really nothing different from what I showed you before. But now, if you really believe that this is a probability, you can look at other moments, for example, the second moment, okay? Or try to get intervals. And so this, if you want, yesterday, just to connect with what you saw yesterday, this guy was talking about the Gaussian processes, and good timing. Thanks, Thomas. And, but does it work? No. Well, we don't tell him. Yeah, well, I don't know. So he was talking to you about Gaussian processes. Well, in some sense, this is no Gaussian process. It's just a maxima posteriori. And then you can go on and look at other moments, because this is just a Gaussian. You can compute it in closed form. And this is the simplest Gaussian process, where the covariance function is just the linear kernel. If we do whatever we did, moving from a linear kernel to nonlinear kernel, and then you view it from the perspective of probability, this is what you call Gaussian processes. Okay? So for those of you who are not familiar with Gaussian processes, you studied, that for like 2 days, and it was just, I got a lot of that now. Nice, this will work. Thanks. So no, I have to turn it on. Up. So this is just to say, we don't talk about probabilities. Of course, there is a lot there. It turns out, as I was saying yesterday, that while at the beginning the point of view are very similar, for social reasons, the people that have been developing these two different perspectives, probabilistic ones and the non-probabilistic ones, don't talk to each other that much, and they develop their own obsessions and preferences about what's important in a problem. Okay, but if you take a fresh start, I invite you to see the commonalities more than the differences, because really, to begin with, the story is just the same. In one case, you say, I only care about the maximum of just one function. No, I actually care about the whole distribution of values around the function. Okay, oftentimes for people that don't take the probabilistic view, the way you get intervals, estimates around a prediction is basically by bootstrapping, by repeating in some way the estimation procedure multiple times and then tweaking mean and average, okay, which is a simple procedure. All right, so unfortunately I cannot delete this anymore, but we can hide it a bit. Okay, so this is just a small parenthesis. What we want to do today is talk about sparsity. And in fact, yesterday you were bombarded with talks that were talking about this. So basically, today and, the first class and the second class this morning, I'm going to cover quite a bit of what you heard Alessandro Verri and Massimiliano Pontil talking about yesterday. So let's just put sparsity in the big context of this course and generally in the machine learning context. We've seen that if you want to learn from data, you have to make assumptions. Okay, that's one of the take-home messages of the no free lunch theorem. If you have a finite amount of data and you need to learn from that, then you have to make some assumptions. And the way we make assumption is basically by introducing regularization terms, okay? They reflect our beliefs about the problem. Or by defining suitable dictionaries or kernels. These are the entry points of our prior knowledge about the problem. You get the data, and then by choosing the dictionary, the kernel, and the regularization, we have channels to fit the problem with our prior information about it, okay? Today, we are going to substantially extend the class of methods we can handle to introduce prior knowledge, okay? We're mostly going to look at linear model, and we're going to work hard to generalize how we can choose a regularizer, substantially, okay? And of course, you can write whatever you want here, but the question is, why does it make sense? What kind of computation it leads to? And here we want to see that basically there is a large class of regularizer that somewhat shares some common idea. And we're going to start from a basic one, the L1 norm, and then we're going to develop on that and see how far-reaching this idea can be. The keyword, if you want, in the last couple of days has been mostly smoothness, or this idea that sometimes my function doesn't change too much, or it doesn't have a big budget. Here we're going to take this last point of view even more seriously, and we're going to introduce the notion of sparsity. So what is sparsity for you? Well, usually that you got something, and this something has a bunch of zeros inside rather than numbers, okay? More generally, we're going to use sparsity somewhat. I'm often going to use sparsity in a slightly more general way, just thinking that I have something that depends on few building blocks, okay? And the exact way in which I say few and building blocks is going to change a little bit. But the basic idea, if you want, is the usual idea of learning from high-dimensional data. So you have that in some sense, you have not enough information to solve the problem, and your hope is that, in fact, you need less than that. You need less than that because your data have some, or rather the model that generate your data have some structure, okay? And here the structure is going to be, while my problem looks complicated, in fact, there are only so many building blocks that can describe it. So if I can figure out those building blocks, I'm good to go. Why is this idea of having few building blocks important? Okay. Well, one perspective is statistical. Why? I just said it. You have, say, few data points in very high dimension, but truly they depend on few parameters. So if you can figure out those parameters, in some sense, the high dimension is doesn't really matter that much. Okay. If you can figure out the real parameter, then you're good to go. This is one perspective. What are the other ones? They're written over there, so you can just read them. But what do I mean by that? What does it mean interpretability, for example? Yeah. So what she just said is that, for example, in biomedical applications, I would say, in fact, most application in biology, oftentimes you are not only interested into making predictions, but you actually want to understand the underlying phenomenon, okay? And you would like to know what are the basic factors that allow you to make predictions. One reason is because oftentimes the goal of machine learning is not only, so in some sense you have the artificial intelligence point of view where you get the data and you want to build a system which is going to be an intelligent doctor that is just going to look at the world of the internet, and you ask a strange question, he's going to provide the answer which is better than your real doctor. Okay, this is one side of the story. The other side of the story is when you look at machine learning as a bunch of tools that allow you to look at the data, instruments like what do you call it, telescope, you know, something, a device that allows you to, or a microscope, even better, yeah, that allows you to look at the data. Okay, and through these tools you can look at the data and get some partial view of them, and this is not just the end of the story, it's one evidence, and then you go on and you use some other instruments. So often doctors, for example, and people that look at biological data use machine learning this way. They get some information, for example, what are the interesting variables, what are the interesting genes, what are the interesting factors in a problem, and then they go on and keep on going and try to make further measurements and further studies to elucidate on the real nature, for example, in a disease, okay? So machine learning oftentimes is just, if you want, advanced statistics in that sense. It just allows to get views of data. Yeah. And in my view, perhaps this one point is really one of the key points of, in a lot of problems of, one of the key use of sparsity. While, yes, in principle, sparsity is really useful where you have high-dimensional data, in a lot of applications I've seen, if you just use, say, ridge regression, that's also good enough to deal with high-dimensional data. But if you want to get interpretability, you will see today that ridge regression falls short, while sparsity really allows you to, as she said, get these important factors. Finally, I wrote here compression. What I mean is that, of course, if you have a big model, you have a lot of variables, and now you can say that, you know, out of these 10,000 variables you have, you can actually kill, out of these 10,000 building blocks, you can kill most of them and be left with 10. That's good news, because it means that now you just have this much smaller model to use. And for example, if you have to now make a prediction, it means that you're going to be much faster. And maybe you can even exploit it while you're doing estimation, because maybe along the way you can say, well, I have to deal with a huge problem, but really, as I go on, I can just concentrate on a smaller subset of the whole problem. All right? So these are three different reasons why it might be good to investigate a bit more the idea that the problem we're looking at might depend on a few building blocks. How do we define sparsity? Well, the basic notion is going to be the one which is written right there. We are going to go back to linear models, so that we basically have just a linear function, and we're going to say that that function is sparse if the coefficients that appear in the linear combination are not all different from 0. In fact, we kind of have in mind the case where only few of them are different from 0, and the majority of them will be actually equal to 0. So the best possible function, or the idea when we're doing machine learning, is that the best possible function we're looking for, that the one that we cannot compute in practice, because it will depend on the whole probability distribution, does have this shape. Or it can be well approximated by a function of this shape. So a linear function with few coefficients different from 0. So when we talk about sparsity, for a while we're just going to talk about this. Of course, now you can say, well, but this is a huge assumption, right? Because we're assuming a linear model. Well, as you can imagine, in fact, if you take any dictionary, so any dictionary of features, well, you can also put sparsity on those coefficients. So instead of putting sparsity on the variables, you put sparsity on the features, you can easily generalize this. And this is one of the original motivation for this kind of stuff. The classical example is if you have a function that looks like this here, but then, you know, and maybe it looks much more wiggly here, maybe it is something like this. The idea here is that if you just use, say, something like sine and cosine, you will have to sweat a lot to describe this, but they will actually be pretty good to describe something like this. But if you now take another set of building blocks function, for example, function that looks like, you know, Gaussians very small or pointy things, then you can describe these very well while you have to sweat here. The idea is that if you take now the union of this, and the sine and cosine, you will just need some sine here, one of the pointy function here, and you're good to go. So in some sense, the idea is that one of the original motivations to look at sparsity is, I don't know, is a kind of a kitchen sink-like approach. I don't know what are the good features, so what I'm going to do is I'm just going to take a lot of features. And in this redundancy, I hope that I capture the special properties of the function I'm looking at. Compare this to just saying, I'm going to build an orthonormal basis. It's much more restrictive, right? Of course, notice, so 2 comments are, from most of our purposes, whether we put here xj or phi j, say for all the computational aspect, it won't matter, okay? So we're going to restrict ourselves to linear model, because otherwise it's basically going to be just a change of notation. Instead of x, you have to put the vectors, which is the feature vector. Okay, so I'm going to restrict myself to just a linear model notation. Notice that there is a huge difference in the fact that the notion of sparsity depends. So we always said that choosing features is important. But here we're taking a step further because the notion of sparsity is conditioned to the choice of the dictionary. So when we take the linear model, we are sparse on the input variables. Okay? So by putting one wj equal to 0, we are saying that the jth coordinate of the input vector doesn't matter. Correct? But when we do here, what are we doing? Well, we don't say anything about the coordinate of the input vector, but we say that the jth feature in my set of features doesn't matter. It's obvious, right? But you want to think about it once. And if you choose a different set of features, or even if you just rotate the set of features you have, you get, you lose sparsity, for example. Really, the notion of sparsity depends on the basis or the set of features or variables you choose to define sparsity on. In fact, you will see that it will be very hard, and there won't be very definite solution to the question of whether we can make something which is sparse and non-parametric. So can we, we sweat a little bit to try to introduce kernel and the whole idea of non-parametric. Here we are going back to parametric models. At some point, can we go back and combine the idea of sparsity with non-parametric? And the answer is kind of, okay? It's not easy to write down a sparse kernel method. And we'll have some partial answer to that. But for today, most of the day, we actually restrict ourselves to linear models. And if you want, you can think of linear model as a general example of something like this. So also in what we have in mind is really the situation where we have high-dimensional data. What do we mean by high-dimensional data? That the number of points is less than the number of dimension. So we're going to mostly look at least squares today, and you can basically see in the background a linear system. You call X the data matrix, you have n rows, the examples, and you have d columns, the variables. And then basically to estimate the coefficient of the linear system, or if you're one of your linear model, you kind of have to solve this linear system. And notice that here you have an equation and d variables. So if you begin like this, there's no hope of going anywhere, okay? And so from the beginning we said, well, probably really this is not what happens, okay? It might be, for example, that a lot of the, what we've said so far is that probably a lot of the entries of this vector are related to each other. This is kind of what we discussed. The variables are related to each other. Here we're saying something slightly different. We say, actually, there exists an ideal vector that solves this problem where most of the entries are actually zeros. Well, but then the story is a bit different, right? Suppose that I come to you and I tell you the indices of the entries that are different from 0. Then what would you do? Assume you're awake. What would you do? A what? You just kill, you have 10,000 columns, but now I told you that only, say, what is it? 1, 2, 3, 4, 5 of them will matter. So then you go in, you select the columns, and then you just let everything else go. But then suppose that you have 10 points, 10,000 dimensions. Now you have this huge, crazy system, but once I told you the entries, you can just go in, pick up those, and you have a 10 by 5, which is in much better shape, okay? So our game, if you want, today is going to be, what can you do if you know that there might be 5, but you don't know where they are? And you don't even know if they're 5 or 10. Okay? But you hope that there are not too many. So the classical idea, the kind of situation you have in mind, that of course we have to question how reasonable it is, but the kind of assumption we have in mind is that D is much larger than N, but this sparsity level is going to be in between N and D. Okay? Or rather, no, it's going to be lower than N, sorry. So you have more points than non-zero coefficients. Okay? So the classic, what we've seen so far is something like this, ridge regression, where you put here the squared norm. Sometimes this 2 is going to appear and disappear, okay? It doesn't matter. This is the squared norm. Yep.
What do you want to be lower than n? N
Just n. Well, so let's say when you look at something like this, the whole idea would be that you need a little bit, you need something d of the order of n, n of the order of d. If n is of the order, the classical, suppose that you have no, well, what he just asked me is, why do you want it to be smaller than n? Is n just fine? Okay. The background of his question is, suppose that I don't tell you that you have sparsity. The classical rule of thumb is, if I have to solve this linear system, I have so many variables, I need so many equations, right? So n has to be equal to d, and everything has to be unrelated, okay, or linearly independent. So what he's saying now is, well, if now you kill everything, you now have n by s, where s is the sparsity level, and it's the same story. You're perfectly right. We'll see that, in fact, we pay a bit of a price here and there of not knowing where these things are, and we will need s to be a bit smaller than n. Okay? So how do we go? Now, what we want to do now is assume that you have this. How do you exploit this assumption? How do you turn this assumption? We just made an assumption, right? We assume that the vector, I don't give you this vector. I give you this matrix, I give you this y, but then I tell you that it should look like this, but I don't tell you where they are and how much the coefficient value should be. But we want to turn this assumption into an algorithm. So what do we do? For now, we take just a penalization approach, and we do the following. We just take the least squares, and we replace, what did I do? See, if you're Italian, you shake your hands too much. And you replace the L2 norm, for the time being, with what is called the L0 norm, which, confusingly enough, is not a norm. But it's easy to explain what it is, because what it does is that it's a functional that, given a vector, count the number of non-zero coefficients in the vector. Is that clear? So read this equation. This equation says, fit the data using a linear model depending on a vector, and try to find the vector with the least number of non-zero coefficients. Make sense? This is the fitting term, and this is counting. If you see here, it's just counting how many non-zero coefficients you have. So it's quite intuitive that these two requirements are going in opposite direction, right? In the extreme case with lambda is big, I'm going to force this vector W to have all entries equal to 0, and I'm going to be very bad on my data. In the other case, I'm just ignoring that. Now, how do you think we can solve this problem with the zero norm computationally? This is a tongue-in-cheek question. How can you solve that? You cannot. You cannot because basically this is pretty nasty, right? What would you do? I mean, you take the gradient of this, and then you look at this, and you do like, bo. Bo is a very useful Italian word if you have to learn more. B-O-H, it means, I don't know, bo. Because this is not nice in all the possible way a function can be not nice. It's non-differentiable, it's non-convex, and so on and so forth. This is a horrible problem. And in fact, it turns out that this is a hard problem in a combinatorial sense. And it's equivalent to what you might call the best subset selection problem. So read this title, try to guess what it is. You have to find out which variables are important for your problem. How would you do that if you have an infinite computers? If you have, God's computer with infinite amount of CPU, what would you do? Try them all, okay? And the classical way you can do it is you try every single variable, then you take all pairs, then you take all triplets, and then you keep on going. And then if you're God, you're good to go. And this is exactly equivalent to solving this problem. If you could solve this problem with the zero norm, it means that you're God. In general. Okay? So we're going to introduce actually two ways to solve this problem in an approximate way. The first one is greedy method, and the second is convex relaxation. The interesting bit that I'm actually going to quickly touch upon is that while this problem cannot be solved in polynomial time for any generic problem, in the worst case, there are some interesting large classes of problems where, in fact, it can be solved in polynomial time. So no paradox here. I'm just, instead of saying all possible problems, I'm going to find out a subclass of all possible problems where I can solve the problem in a computational efficient way, and it will turn out that either one of these methods will do the job. And I'm going to mention a little bit in passing what are these class of problems. But for now, just think that you just want to go for an approximate solution to this original problem. Okay? So what do you think is going to be a greedy method? Well, we just described a method where what you do is that you try everything. All single variables, all pairs, all triplets, all quadruplets, quintuplets, sextuplets. But you cannot do that. Now you have my laptop. So what do you do? Giovannino, what do you do? Like, come on, I mean, you've been here for 3 days now, you must have a guess. Mickey, what do you do? What do you do? If you want to do something that's called greedy, yeah?
Find best one for we have just one subset with one element.
Yeah.
Then we take this best element, then we look at all the others and look at which combination is best with this element we found. And then we go on like this.
So I repeat the first thing you said because I understood, then you repeat the second thing because I didn't say. The first thing you do is that you select one variable. Then what do you do?
We fix this variable, and for the possible two-element subsets, we always keep this variable in.
Right.
And then find the next best.
Yeah. So that's the basic idea, okay? So what he said is, instead of doing all ones and then all pairs, that's too much, okay? You do all ones, and then you do all pairs where the first one you picked is one of the pair. Now you have to just add one, okay? So you kill the problem substantially from a computational perspective. And how do you keep on going? When you need 3, you're not going to try all possible triplets, but you're going to take first the 2 ones that you already picked, and you just try to add 1. That makes sense? Clearly, this is going to be much less than the original goal, but that's why you call the greedy method, because you start along the way, you add something on, you hope that everything goes well. It's pretty clear that you're going to produce a sparse solution this way, if you don't have to go all the way down to the end. And the class of greedy methods can exactly be described by this. This is just repeating what we just said, okay? It's basically saying you have to initialize something at some point, then you select, then you compute the solution, then you update everything, and then you keep on going. Let's look at the basic example, which is what you might call either matching pursuit or basically a form of what is called in statistics forward stage-wise regression. So the notation is slightly annoying, but the idea is super simple, okay? So what do? The first step is that you solve the problem with a single variable, just one variable, and you pick the one with the best error. So at the first round, you want to try to fit the vector of outputs, right? So you take y. Look at this footnote. The important part of this slide is in the footnote. So Ri minus 1 here, think of it as the output vector, not at Ri to the minus 1. It's just the output vector. Then what's written here is that this is just a column of the data matrix. So it's the jth variable. V is just a number, okay? Because this is every column here is of size n. I want to now fit the output, which is also the size of n, and then I'm just trying to rescale the column. If you want, if everything is normalized, I'm just trying to find the column that is best correlated with the output. Here, I might not have normalized things. So you find the V for the columns j that give me the best error, and the error is going to be this quantity. Now, here, if you take the square, it's easy to see that you get this. So what's written here is just that it's a more compact way to rewrite what I wrote here. And I just wrote it this way because this is the standard way you see it on Wikipedia, say, the ultimate source of all informations. You see this equation, and oftentimes you don't even see this because you normalize the columns to be 1, which is important, okay, as we comment in a minute. So when you see this, you should just think that these 2 lines are in fact exactly the solution of the least square problem with 1 column at the time, and the value of the least square error with that 1 column. So you say, give me the column, or rather the corresponding variable, that gives me the best error when you try to use that 1 column to predict the output. Okay? The first step is going to be equal to everybody. Does this make sense? Is it clear to everybody? Yep.
So minimizing the AG, the error.
Say it, well, just 1 second because I'm hold.
AG is the error, right?
AG is the error.
So what do you minimize this error?
So,
I don't understand why it's maximizing.
so look at here. Okay? You say, first, for each variable, so this is what he's asking is, are you maximizing or minimizing what's going on there? Well, first you minimize what you minimize. For each column, the error. So then for each column, you get an error. Now you have an error for each column, and you want to still minimize it. But I made a mistake. AJ minus is equal to xj vj minus y or ra minus 1. Okay? So there is a mistake there. AJ is not this, but there is a minus. Basically, the way you go from, the way you do this is just you take the square. So this is just an AJ. And then you see that a bunch of things cancel out, and you just get this term. Okay? But yes, there is a typo. It's one, I skipped it, but it's just half a line, so you can double check me. But there is a minus here. So minimizing this corresponds to maximizing AJ. If you want, just to convince yourself even a bit more, here I'm minimizing the error, but because I'm in one dimension, minimizing the error is like maximizing the correlation, and AJ is exactly the correlation coefficients, which turn out to be minus the error. So maximizing correlation or minimizing the error is the same, and so that's what I wanted to write here, and so there should be a minus there. Okay? Yep. More.
There is a minus there, AJ should be always negative. And how can it be equals to V there?
You should have done the calculation while I was speaking so that you can tell me the answer. Now we have to do the calculation. I don't know. It's like that. Let's see. So you get xj v j minus y, let's say. You want to minimize this. You take the gradient and you get twice x. Do I put it up or down? Down. xj transpose xj v. This is a generic v, okay, minus y equal to 0. Then I get, this goes away, and I get x transpose j xj v equal x. So the answer is that A doesn't need to be positive, okay? But now we also rewrite it because I'm upset and I have to show that I can do squared very well. Right? So we do this. This is just the norm square of xj. Can you see more or less up there, Giovannino? So vj, the one that solved this, is going to be x transpose yj minus xj. But now we're on a roll, and so we can even go back and substitute in and see what happens, and you can tell me the answer. So we do it here. Hopefully, we will get what I promised. So xj, and now we get this guy. Did I write it correct? Here. Good. So now I have x j. So remember that this is a vector, okay? X. So there is a hat everywhere. Hat. Transpose hat. Okay, from here, I guess you can kind of see what's going on. You take the square of this, okay? Let's do it. This is just a number. So you got this number squared. And then here you got this norm by itself. So you get x transpose j xj times x transpose jy okay, square. But this is a fourth that goes away with this, which is just a 2. Okay? I mean, you should just correct me because I'm the only one who has problem because I cannot see one symbol, but for you it should be easy. Then what do you have? Then you have this guy, but this guy don't care because it doesn't depend on anything I care about. Okay, so I can just, it's just a constant. I'm gonna minimize, so it doesn't matter. So we just have to check what happens with that thing, I don't know how you call it in English. Cross product. What happens? You get minus twice, this times that. But what is that? Well, it's minus twice xj. Again, this is just a number, okay? So I write that number down. Almost. So this is the number, but then I still have to do xj times y. So I get this, but this is just this times this. So it's again, it just is exactly equal to that, okay? So this goes away, this becomes a 2, and here I have the same thing, right? So now I have that this is equal to minus xj transpose y square divided by xj square. Correct? And then I'm confused again. Yes. Yeah. I guess that's it. This is the correct final form, right? So it's not the objective function which is the same, but is the value of the minimizer and the maximizer, because while because now I hope it's clear. Okay? So it's not just because there is the inner product, because in fact the inner product is a square, but it's because you add the square norm, and in the end that quantity is going to be positive. Okay? Because this is an equality, because we proved it. We proved that it's positive, because this is an equality, in fact. Okay? We good? No, we did it. What do we have to do? So you let me do this, but this was not the question. No. So let's say, forget about what's on the slide, okay? Look what I did here. Okay, I'm just saying, you have to minimize this, okay? And here we show that this is actually equal to that. So you can also maximize, because you have to minimize this doesn't matter, and so you just have to maximize this. You agree? That's it. And I call this whatever I need to call it, AJ, okay? Good? I'm going to fix the notation, but the board is double-checked by you, so it must be correct. Okay, so sorry for the mess. This is the first step, and the only problem with this step is the notation, okay? And that's why I made a mess. And notice that here I put y hat, because it was the first round. In general, and in fact, you see at the beginning, this r is exactly just the y hat. But at the second round, what you might do is you want to shave off how much you already explained of y, and then just try to explain what's left. So r is the residual. At the beginning is just the vector. The second time around, you just take out what you explain of the vector you're trying to predict and select the next one variable that can give a contribution to explaining what it is. So this is the selecting step. Here I'm mixing up the computing the solution and the updating step. So capital I is the active set of variables, so you just have to add 1. So that's what's written there. At the beginning it was nothing, now you add 1. Then in the simplest version, what you do is the following. What's written here? You take a vector of solution that contains only 0 at the beginning. Then you compute a number that corresponds to one entry. And what's written there is that you go and you put this number in the right entry. So the way you do it is just that you take this number, you multiply this by the element of the canonical basis with that 1 in the right position, and then you add it. The second time you do the same. Now you have a vector with one entry, but you're going to take another vector with the right entry somewhere, you sum them up, so you fill in another entry. So this is a way to fill in the right entries. Notice that what you do, it is at each step, you don't recompute the solution that you already computed for the variable you took at the first step. So the first step, you take a variable, you compute a coefficient. The second step, you take a second variable, and you just update the solution, adding one coefficient. But the previous coefficient is untouched. Once you've done that, you compute the residual. And the residual is just going to be exactly what I said. The first round, you take y, and then you subtract the contribution of the corresponding column. And then you keep on going. Matching pursuit is kind of a pimped up version of that. What you do is the only difference is basically that at every step, what you do, again, the notation is slightly annoying, but just saying words, it's fairly easy. At each step of the algorithm, you will have an active set of variables. Just recompute the solution on that active set of variables each time. It is going to be a least squares, only restricted to the columns that you selected up to that point, right? So what's written there is just a notation to say, well, each time take the active set. The way you select variables is just the same as before, the one we spent some time to correct on the board. And once you have it, select the variables, add it to your active set, and then just solve the problem on this set of variables. If you think it's going to be safer, okay? Because what might happen, why do you think, well, why do I think that this algorithm might be safer than the one before? Because the one before, what might happen? At the beginning, you just select one column, okay? You ignore everybody else, and you get the coefficient. Maybe a single column is not good enough. You really have multivariate effect. Okay, you really have that you have to take two columns at the same time. So if you force yourself to just take one, you might take one, and this might be not good enough. So at the beginning, you might make bad estimates, and then next time you don't recover from that anymore. You can just try to, well, you can recover, but you sweat a lot because you have to take new variables to somewhat balance out the mistake you might have done at the beginning. Not the mistake, but the suboptimal choice, exactly. The suboptimal choice that you've done at the first step. What you do here is that each time you actually check whether you were doing, in some sense, whether you did a suboptimal choice or not, because each time you recompute the coefficients. Okay? And in fact, each time you can go on and select the same coefficients more than once. So you can go in and double check what you want to do with these coefficients. These are the, is it clear? So the scheme is fairly simple, and if you want, the second one is a bit more principled and a bit safer than the first one. It's called, and the second one is called orthogonal matching pursuit. These are just two examples of a long family of algorithm. It's forward in the sense that you go greedy by adding one at a time. There are techniques that go the other way around. You go backward. You take the whole thing and try to shave it down. Of course, here, from the discussion we were just having, it points out to the idea, well, maybe what I want to do is to want to add one, then I want to compute, and then really check if I need it. Maybe otherwise I throw it away, and I want to go on in a forward-backward kind of way, where I put something in, I check, then I throw it out, and so on and so forth. Okay, so there are tons of variation over this idea, and these two are just the basic ones. What are the free parameters of this algorithm? What is the free parameter of this algorithm? Enrico, what is the free parameter of this algorithm? Yeah, there's not many choices. Where you stop is the right one. Does it make sense? Well, let's go back here. what do you expect the parameter? The parameter here does what? It decides the amount of sparsity in the solution balanced out with the mistake you make. Here, it kind of makes sense. We won't prove anything formal about it. It kind of makes sense that this guy is basically doing the same thing, because each time you try to reduce the error, but at the same time, you're typically introducing a variable. So when you start with t equals 0, correspond to lambda equal to what? A qualitative speaking. If you start at the beginning with t equals 0 or t equals 1, correspond to lambda big or small? Big, because you're basically throwing away everything. If you keep on going, the idea is that it corresponds to lambda smaller, because eventually you're going to look at all the variables many times, and eventually you would like to be able to show that something like this gets close to that combinatorially hard solution. Okay? So if you plot, say, a cross-validation curve with this t in the x-axis, you should see the characteristic shape of a learning curve with the minimum and so on.
Here it's at step E, it's at step E minus 1, union G. We should not, because I think the difference between this method and the other one is that we add here a combination of columns at each time.
Yeah, but there I'm just keeping track of what is the active set, right? So I just check what I already selected. And each time I have to solve the problem what I selected. And the selection criterion doesn't change. So what is it that you would like to change? No. No, each time we add one column, period. And that's what we call the active set of columns. But we recompute the solution for that column we selected and the one that we already selected. So the coefficients is what you recompute. Okay, so so what he's saying here is that you can add one column or a combination of columns. No, you always add a column, but then you recompute the coefficients on all the columns that you selected so far. Whereas before, you were keeping the solution, the vector W here completely change potentially at each time. Whereas the vector W here, you only change one entry at each step. This is the one difference, okay? Okay. So much for greedy methods. Yes?
So is matching pursued now again spectral regularization in the form we discussed on Tuesday or not?
No. So his question is whether we can view I like this, so it's going to take you a parenthesis, unfortunately. So the question is, we discussed on Tuesday the idea that by doing early stopping, you can achieve regularization. Okay, and the way we explain this is by taking a point of view of spectral regularization, where we're throwing away eigenvalues. So his question is this a form of early stopping / spectral regularization? And this serves as an opportunity for me to ask you a question. Is ridge regression a sparse method? Not just L2 regularization, but ridge regression, or say TSVD. Let's say TSVD is a good example. Truncated singular variable decomposition, you remember? Is it a sparse method or not? Yes? No? Well, it sets some coefficients to 0. Okay, to some extent. So if you remember, what he assumes is that the function we're looking for can be written well on a special basis. Which one? All the spectral methods throw away the... Which means that we are basically assuming that the function we're looking for can be written well on the basis given by the principal components. Not only that the first few principal components are going to be more important than the last few. If we make a stronger assumption, we say that the last few don't matter, this is just a sparsity assumption. Correct? So in some sense, in ridge regression, TSVD, we're making a form of weak sparsity, but it was sparsity. It was weak because rather than assuming that the coefficients on the principal components are exactly zeros, we're assuming that there could be decaying or small, okay? But rather than this aspect, the point which is important is that in that case, we were assuming the important basis to be the principal components. So as I stressed at the beginning, the notion of sparsity is always conditioned to the choice of a dictionary. So here we're working with the generic sparsity. We use the case of a linear model, so we assume the canonical coordinate. Where is it? Here we're assuming the canonical coordinate to be the prototype example, but we could think of taking here any dictionary. If you take as a dictionary the principal components, then what we saw on Tuesday could be seen somewhat as a sparsity method. Is it clear? So the take-home message is, whenever you do, even smoothness can be seen as a kind of form of sparsity on a suitable principal component basis. But here, we're taking, so it's not the other way around. So while, in some sense, spectral regularization can be seen as a form of sparsity over the basis of principal component, the opposite is not true. It's not true that any sparsity method can be seen. So in some sense, the name spectral regularization is reserved for the sparse method. Spectral regularization is reserved for sparse method choosing the principal component as the basis of choice. Make sense? If you want a different question, is a slightly different question, which, so if you want in this sense, the answer is no. But there is another sense in which the answer is kind of yes, which is, but can I see this as a kind of form of early stopping, where you add greedily things and then at some point you stop? Yes. In that sense, it can be seen as a form of some kind of iterative regularization, if you want, or early stopping regularization. Not spectral, though. So we introduced, yep.
Maybe I'm confused, but in this case, the sparser solution is more biased or more?
More biased. Yeah, you see from here. So bias typically means that you are regularizing more. So typically, let's say, so Enrico is asking which is the more biased solution. So what do we mean by biased solution? If you put lambda equal to 0 and you just solve the least square problem, you know that if you get infinitely many data, you get to the right mean. And here you're basically saying, well, actually, strangely enough, I don't want to do it. But I don't want to do it because I don't have infinite data. I rather introduced a little regularization. You can view it as a bias. So if now you let the number of points goes to infinity, this doesn't go to the right place. But that's because typically you also want lambda to disappear if you get enough points. So the two ideas are not in contrast. The idea is for finitely many data, we introduced a little bias that is going to stabilize everything. And of course, if you give me more data, I should let this bias disappear. And so if lambda is big, there is more bias. If you go now to the iteration, we already answered this question. The idea here is the more you go on, the more you're going towards small lambda, because you take variables in, you fit more. So in that sense, at the beginning, you have a big bias. You're ignoring the data in favor of very few variables. But the more you go on, the more you insert variable and you start to fit. OK? OK, so, oh, it's super late. We have sparsity. We have matching pursuit. Matching pursuit is by far the simplest way to solve sparsity. The other way is convex relaxation. So what is convex relaxation? It's not this, in fact. You have the L0 norm here, not the L2. You have the L0 norm, the one you would like to solve, but it's counting the coefficient is not good. So what you do is that you replace the counting by the sum of the weights made positive. So before, we were saying, look at the W, and if it's positive, count 1. Here we're saying, look at the W and just count W. So if it's positive, if you just take the absolute value and you sum it up. If it's 0, it doesn't count. But if it's positive, you just count it for the size it has. OK? So it's a relaxation. rather than just counting 0, 1, we now count a real number. As a side comment, one thing which is important is that here, clearly, you can mess, if you don't normalize the column of the matrix X, you can arbitrarily change the weights, okay? Imagine that you have two columns that are the same, and you put some weights, W, on them. Then you arbitrarily multiply the first column by 100 and divide the second column entries by 1,000. Then you can clearly change the W's artificially. So here in somewhat is important that at the beginning we need to normalize the columns so that we get, if you care about the order of the scores, if you care about who's 0 and who's not, it's okay. But if you care about looking at the coefficients and say, oh, this is bigger than this, then you need to normalize the columns. Otherwise, you can mess things around. So this is a small comment. We can take it offline if it's not clear. So the idea here is, let's replace the 0 norm with the L1 norm. So we want to do two things. One, convince ourselves why the hell putting here the L1 norm would give me a sparse solution. I want something that has exactly 0 coefficients, okay? I could have put here the L2 norm. So why is that not enough? Why L2 is not a good convex relaxation than L0? It is a relaxation, right? I take L0 and I put the square norm. But why is it not good enough? Is the question clear? That was, I have L0, and we convince ourselves that L0 gives me a sparse solution. But it's computationally not feasible, so I need to look for something else. I claim that I need to put L1. And first of all, why is the claim true? I also claim that if you put L2, it's not good. Why is this also true? Make sense? Well, to do that, we're just going to take a simplified version of this, where we assume that we can just find among all the solutions of the linear system, the one with minimal L1 norm. How many of you have seen this picture before? It's kind of hard to miss this picture if you've seen any talks in the last 10 years, because sparsity is one talk out of 2, and this is in every sparsity talk, so you typically have seen this before. The idea here is this dashed line is the set of W. It's a toy picture, okay? So you have to understand a bit, you have to use a bit of imagination. You want to take a linear system where you have multiple solutions, okay? Because you have too many variables and too few equations. And here I represent this by this red dashed line. These are the set of all possible W's that satisfies this linear equation. Because it is a linear equation, I can write them down as a line. Then and so this is fixed by the data. And then I have to find the minimal L1 norm. How do you write it down? Well, you can convince yourself that the shape of the L1 norm is just a diamond, okay? But in fact, it's very easy to convince yourself that if you use the squared norm is a circle, because it's x1 square, x2 square. Here you have to take the modulus of W1 and the modulus W2, and so you get exactly something like this. So what does it mean graphically to solve this problem? Well, first you find a set of solution to this linear system, this line, and then you write the diamond and you inflate it. Okay, you take it bigger, 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 or if you want, you take it smaller, 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 until you just hit this in one point. And then boom, that's your solution. Okay? Because it's among all of them, is the minimal one, is the smallest one, that gives me one solution. If I make it a little bit smaller, it doesn't have any, there is no W in this set. But if I make it a bit bigger, I have more than one, so it's not the minimal one. So I have solutions, but this is not the smallest diamond. So these pictures show you the minimal L1 norm solution among all the solutions of a linear system. Giovannino? Eric? Enrico? Alexandrina? And Luigi? Why is the solution sparse? Well, because it is. Where do you have the touching point? Well, usually you have it in one of the corners of the diamond, right? Either up, right, blah, 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 blah. But each of these points is going to have just one coordinate equal to 0? No. Different from 0, and the other one equal to 0. And if you go in higher dimension, you can see that the same effect always happens. When do you have more than one solution? Only in the case where the slope is exactly 45 degrees. So if you throw at random, suppose that now you choose at random this x and this y. Okay? You just choose them at random. These are just problems. And now you check whether the set of solution is 45 degrees. So I say n is equal to 10. The number of features is equal to 1,000. Just create a random problem. Is it going to be 45 degrees? Well, it depends what you mean by random. But if you say, if you take Gaussian random numbers, probably not, right? Do you see what I'm saying? I'm just saying the fact of not being at 45 degrees seems to be a pretty generic property. You have to put some effort to put yourself at 45 degrees. And this is as far as I want to go in explaining you why. And this reasoning actually extend, though, as you can imagine, is trickier in higher dimension. An L1 ball is no longer a diamond, but it's a polyhedron, a diamond with more shapes. So you have more faces that and this becomes potentially a line or a hyperplane. So the thing is a bit more complicated. But the bottom line of the story is that you can quantify exactly when this happens. Okay, when this, you know, what is the probability of not hitting a corner or a few corners? Forget about that stuff for a minute. I'm going to mention the condition in a bit. But the point here is that you kind of see why, at least in this simple situation, L1 is going to give you the same solution as L0. What is L0? Well, you have to basically bend each of these inward until you get a cross. That's L0. Okay? L1 is this one. L2 is going to make each edge fat. And L1 with LP with P smaller than 1 is going to bend the edges. L0 is the case where you just have the cross. So if you put here this cross here, it's going to intersect the line exactly there. And you kind of see here that L1 is just doing the same. So in some sense, this says that it's kind of, you start to see a structure where you say, well, unless I actually going to put myself exactly at 45 degrees, I'm good to go. L1 is going to give me the same solution as L0. Of course, this is a bit misleading because in dimension 1, in bigger dimensions, say if I give you now 10,000 dimension, then our intuition will tremble a little bit, and in fact, it becomes a little bit obvious to prove it, but you can.
At 45 degrees, L0 would also be 56.
You're right. Yeah. So in fact, there are two problems here. One, so what she's saying is that I'm saying something stupid, which is true. Because if you just put the 45 degrees, also L0 is not unique. So you're lost. So this doesn't really say that. So the condition that tells you that L1, you need two things, okay? So I was a bit imprecise. So to be sure that L1 gives you a good solution close to L0, in fact, you need two conditions. One is that this line is not at 45 degrees. And it's actually far away enough for being at 45 degrees. So you need, in some sense, the solution to be unique, but also to be away enough from 45 degrees that in some sense, when you relax, you don't get confused. Okay? So this is not as nice as I remembered. So let's drop it. Okay? So I'm gonna see if I can explain it a bit better in a minute. Let's go back to the primary observation here, which is that this gives you a sparse solution. This we can agree. And whenever you're not at 45 degrees, it's going to be the same as L0, okay? And I guess the point I wanted to make is that if you just generate the problem at random, it's not going to be at 45 degrees, so L1 and L0 are going to give you the same solution. This we still agree on, I guess, okay? What about ridge regression? Ridge regression is the case where rather than L1, you take L2. And L2 is essentially a circle. I should put a square here, okay? Square norm, the ridge regression. Is it sparse or not? Well, we have to do the same game as before. We take the line, which is the set of solution of the linear system, then we have to take the L2 ball and make it bigger, 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 bigger until we touch the line. Where are we going to touch the line? Well, somewhere, I don't know where, but it's not going to be in a corner. It's not going to be on one of the coordinate axes. Here it's going to be in this point. And this point has a big coordinate and a small coordinate, but they're not zero. And so if you solve that, you still have to go in and introduce a threshold, and you have to decide how to choose the threshold. But it means that now you have more than one threshold, okay? So this shows you how L1 gives you a sparse solution, whereas L2 generally will give you coefficients that might be small, but they're not zero.
Here we try to approach the line, but in reality it's eclipsed, right? Because the minimizer, we try to minimize the fitting term. It's
Yes.
x w minus y norm 2. So
Yeah.
eclipses,
Well, it's gonna be. So if the thing is degenerate, it's gonna be, I guess, an hyperplane, but with some slack. If you assume again, this is a bit simplified. It's just to make the point. So one way to relax is to say, well, I don't want exactly to have this, but I actually want to have all the w that are distance y delta. Okay, so it's basically going to be not only this, but everything which is within a certain delta of that line. Say again? Say it again, sorry?
Is that why you needed to be separated from?
Yes, yes. So you see what I'm saying? So here I'm just taking this as a prototype case because it's the simple one. In practice, here we wrote the Lagrangian formula, the penalized formulation. Instead of jumping right there, we could do an intermediate step where here we say, well, let's relax this, and let's say that this is xw minus y smaller than delta, which basically means that you're still trying to find the solution to solve that, but then you give yourself a slack. You just give yourself a delta to be far away from that line. But more or less, the picture doesn't change. Okay? So this is more or less the geometry of the problem that gives you an idea of why L1 gives you a sparse solution, and actually L2 does not, which is what we wanted to try to do. So the first time you see this is kind of a bit confusing. If you work it out yourself, it's pretty clear in the end. Okay, and there are a bunch of details hidden, but this is as a first order intuition, it gives you one of the best way to go. The second question we wanted to ask is about computations. So you now have to solve this problem, and you're happier than you were before, because L0 was not convex and not differentiable. How about this term? Did I write it? Yes. This term is convex, because L1 is like this. But unlike L2 regularization, it's not convex, because in the middle you have a kink. You have the zero where it's not differentiable. So how do we solve it? So this functional has been proposed, I don't remember when, 95, I guess? The idea of using this kind of function, it's old, but it's kind of popularized around 95, and it has two names in statistics and signal processing. In one case, it's called the Lasso, or Lasso. In that case, it's called basis pursuit. It's kind of the same thing. So if you want to solve this, how would you do it? How would you do it? Miki, how would you do it? It's complicated. We don't even know what it is. We haven't learned it yet, right? We only know what's happened in the last 3 days. You want to do gradient descent? Almost, because you have to call it subgradient method, because it's not a gradient and it's not a descent. But other than that, you can do kind of what we did before. You can try to do the same game. You take this guy, rather than taking the gradient, you have to take the subgradient, this thing where if it's differentiable, you take the gradient, but if it's not, you take, say, the left derivative, and then you do an iteration that looks like the gradient, but you have to take the step size decreasing rather than just constant, okay? You do that, and you find out that it's slow, okay? But then, you go to Sylvia, and she's an open book of optimization, and she tells you that, in fact, if you have to optimize a non-smooth convex functional that has a so-called composite structure, then you're good to go. What do you mean by that? This thing here is not just any convex function. It's actually made of two terms. It's the sum of two terms. It's composite. The first term is convex and smooth, whereas the second term is convex, but non-smooth. So it turns out that all these techniques, all these functional that share this form, convex smooth plus convex, can be actually solved by a class of method that is called forward-backward splitting proximal methods. So the algorithm is very easy to explain, okay, with a twist. So ignore for a minute this line and just consider prox to be a nonlinear, possibly nonlinear projection, okay? So look at this iteration. I'm saying, if you have to solve an optimization problem, a minimization problem, where the objective function is the sum of two terms, and one is convex smooth, and the other one is convex non-smooth, you can always solve it with something that looks a little bit like a projected gradient, in the sense that at each iteration, you compute the gradient of what? Only of the smooth part. And then you compute something that depends only on the non-smooth part. Okay? So right now, you just have to believe me, you can do it, and you should be happy because you have an algorithm that splits the contribution of the two terms that compose your objective function. The smooth one, that is just appearing as a gradient, and the non-smooth one that just appear as something fancier that we have, to take a minute to explain what it is. Okay? Now let's look at this part that depends on the non-smooth term. It's written here. It's called a proximal operator. And this is the definition. You have to minimize, in some sense it looks like regularization in a way. It's a regularized version of the norm, of the penalty. So you take the penalty, you perturb it a little bit, and then you minimize. If you just stop here, does it look like a good idea or not? Do you like this slide or not? So I'm selling you an algorithm. It goes like this. Oh, I see you have a minimization problem which is made of the sum of two parts. How about you take many steps in which at each iteration you solve another optimization problem? And you say, you're crazy. Why just one optimization problem and you want to, it's like, the dishwasher. I mean, I give you this and I give you this, no, it doesn't make sense. I'm now trading you one optimization problem for many optimization problems you have to solve at each iteration. Either I'm crazy or there must be a catch. What could be the catch? Well, if you can solve this problem in a much easier way than this one, then maybe it's a good idea. I'm basically telling you something where you don't really know how to solve it, but if you know how to solve this easily, then you're good to go. Okay? This must be the catch, otherwise I'm crazy. And you know that I'm not crazy. So there is a theorem that tells you that everything goes through fine. There is a theorem like gradient descent. It says you can choose the step size to be a constant. So let's take a quick look. The theorem tells you that basically the step size will depend only on the smooth part. So the condition will look like the condition on the gradient. Okay? But then once you have that, you basically know that you go to a minimizer. Notice that I say a minimizer because nowhere I assume the function to be strictly convex. So there might be more than one minimizer. Okay, when you look at this is convex and this is convex, but it is not strongly convex, okay, or strictly convex. So you might have more, you have a smile with a potentially flat region, okay? So you don't have a single minimizer. You just know that you go to a minimizer, but it's a minimizer. Now, this is the good news, what I promised you, that the proximal operator, for relevant examples, say the L1 norm, can be written in closed form. So the minimizer of this problem can be just written down easy. And in the case of the L1 norm, is this thing here. So this is the prox operator of lambda L1 norm. So what does it do? This is so the prox operator, you enter a vector, and here I'm explaining what the operator does to each entry, okay? And what it does is the following. It looks at the entry. If it's small, where small depends on lambda, it sets it exactly equal to 0. And ideally, what you would like to do is to say, well, if it's bigger than lambda, I just let it be. I just take it, I just leave wj. So a harder thresholding would be, if it's small, put 0. If it's big, just leave lambda. Okay? Before reflecting on the fact that this is slightly different, think of what the algorithm is doing now. This algorithm here is taking a step of the gradient that depends only on the loss function, the squared error in this case. Then it takes the solution that you computed at the step of the gradient, look at each entry, and set it equal to 0, if it's small enough. Otherwise, what it does is that it changes it a little bit. If it's bigger than 0, it lowers it down a little bit. If it's smaller than 0, it raises it a little bit. Okay? The reason why you do it is mostly, again, because otherwise here this operator would have a discontinuity. But there are also ways to try to approximate the hard thresholding. But this is like the basic one for the L1 norm. So in making this observation, and by the way, proving that this is the solution of this problem with the L1 norm is not too hard, okay? Again, you have something not differentiable, but you can basically convince yourself easily that that's exactly the solution. So again, I invite you to try to do this as an exercise. For general regularization, it might be hard, but for the L1 norm, it's easy. So by doing this, we actually now are in a good shape for two reasons. From an optimization perspective, you know that you can solve L2 plus L2 loss plus L1 norm by basically doing something that is a gradient descent plus a soft thresholding operator at each iteration. So you just do this, okay? This is the complete form, where you see that they have to plug in the step size. So we're happy about that. It's a simple algorithm, and you can show that these actually converge faster than the subgradient method, both in theory and in practice. And in fact, people have been spending a lot of time trying to show that you can even accelerate this, the same way you can accelerate gradient descent. Notice that in general, this problem is only convex, okay? The problem is only convex, so you cannot hope to have super fast convergence. The second observation you can make, and then you have another indirect proof that the solution is going to be sparse. Because you can see it from the way you solve it. At each step, you set the coefficients to 0 when they need be. So of course, the solution of this certain iteration is going to be sparse. Where is the regularization parameter? It's here, which also makes sense. If you put an interval very large, everything is going to fall in the interval, and everything is going to be 0 at every step. Whereas if you make the interval very small, everything is going to be different from 0. Okay? And this is more or less it for the main part of this story. Okay? So if you go the convex relaxation way, you can look geometrically at the solution of the problem in a simplified way and convince yourself that L1 is indeed going to give you a sparse solution, whereas L2 will not. If you know down and try to solve the problem, you can learn there is actually a large class of methods there is a nice class of method called Proximal method that allows you to solve problems where you have this composite structure, smooth plus non-smooth, and decouple the contribution of the two. And this method has become very popular because for all L1-like regularization, or for a lot of them, you can compute the proximal operator in closed form. And it has a simple form like this, which makes the algorithm very easy and fast. Not fast, but very easy to use and potentially fast to compute. Okay? Any questions so far? So one question, yes.
Early stopping now poses additional regularization.
So what he's asking is, 2 days ago we did ridge regression. We said you can solve it with a linear system or with gradient descent. And then we said that in fact gradient descent itself was a regularization. And so if you're doing ridge regression and gradient descent, you're doing 2 regularization. Here you might ask if I'm doing something like that, because there is a regularization by lambda, and then there is something on governed by t. So is t here playing the role of a regularization parameter? The long story short, the answer is no, because in some sense the t here is still convinced that the principal component basis is the right one. Okay? So the t here is not playing the role of regularization parameter in general. A slightly different question is, can I now have a black box that does create early stopping algorithm? So I come to you with the norm, with the R, and then you give, for example, L1, and you give me an early stopping criterion, where there is no lambda, but there is just early stopping. Okay? Success orthogonal matching pursuit is doing something like that. But can I really have, say, a gradient-like technique that, at each step does something, and the more step you take, the more you decrease or increase the sparsity? And that you can do. Okay? And this is something we did this year, so I know that you can do it. You can do it both for fairly generic penalties and also for fairly generic loss term. Okay? Yeah, this is the question that were bugging me for a while, and now we're solving it. Yeah.
The gamma can depend on t. Gamma.
So the question is if gamma can depend on t. The answer is that typically you don't want gamma to depend on t because you want to be able to choose a priori a big step size and don't change it. And here you can do that. Okay? And this is the basic theorem I show you. There are a few variations where you can try to get other choices, where you try to optimize it in some way. And in some cases, you can prove it goes in the right place. In some other cases, you can prove empirically, for example, there are things like Armijo rule and other kind of techniques that might give you some speed up, but you cannot prove that they go in the right place. So I'm running out of time, so I'll just list things that I didn't have time to talk about, and then I check if I managed to squeeze them in at the beginning of the next class. So one is, here I'm doing, this one is important, okay? Here you see that rather than leaving the right coefficient alone, the non-zero coefficient, I decrease them a bit or I increase them a bit if they're negative. In practice, you see that this is actually causing problems. And what people often do is that they use these only to select the variable, but then they recompute the coefficients on the selected variable. So they don't believe the coefficient that come out of this. They believe when, only 0 or non-zero, but then they recompute the coefficient. Okay? This is important. In practice, if you want to use this, typically this is needed to get a good solution. This is remark 1. Remark 2. I told you, and we commented a bit, that you might need now a number of points that depends on the level of sparsity rather than the dimension. This is roughly the one equation that you want to remember. Okay? You have that there are the number of points you need to solve this linear system. If the solution is sparse, it's going to be proportional to the sparsity level, and then you pay a price that depends on the true dimension, but only logarithmically. So this is nice and to be expected, because you don't know where the right entries are, right? So you must pay a price of discovering where they are, otherwise it will be too easy. So in some sense, that log D over S is the price you pay for having to discover where the entries are, and if you want also that too, and then you just have to recompute things on the right ones. So this is the intuition about this theorem. And if you want theorem like these, are the basic for a lot of work in high-dimensional statistics and compressed sensing. This result, and this is by no means exhaustive, is somewhat connected to ideas related to Shannon sampling theorem. Shannon sampling theorem tells you that if you have a band, if you have a signal which is band limited in a band which is with the maximum frequency is W0, if you take 2n samples, twice W0 samples, you're good to go. And in making this statement, you're typically assuming that everything inside of the band matters, that all the frequency matters. But if I now tell you that, in fact, yes, you're in between these, but you only have very few frequencies inside, you can hope that you can reconstruct the signal well, even if you have less information, okay, with much less samples. And basically, the idea I show you today can be used to do exactly this, show an effective sampling theorem exploiting an extra assumption that not only your signal is between minus W0 and W0, but also that inside of there, only few components will matter. So there has been a lot of work exploiting this idea. Let me just mention quickly, you can convince yourself easily that if you have variables that are correlated, you're basically putting yourself, you jump into the degenerate situation where you're 45 degrees. If you take two variables that are normalized, the columns are normalized, and they're perfectly correlated, then you put yourself in the degenerate situation. So in practice, this is not going to be as perfect like this, but you can ask yourself, how is the lasso going to be selecting the right solution when I have two coordinates, two variables that are both important? What does it do? Is the question clear? This is, again, another very important point. If you want to use Lasso for variable selection, and you have two variables that are very correlated, what does it do? And the short answer is, both. Depending on the way you initialize, you're going to choose one or the other, or any other of them, because they're good. For him, they're good, okay? And so now the question for you is, but what do you want to do when you have two variables that are perfectly correlated? Do you want to pick one, or you want to pick both of them? I cannot tell you that. This is up to you, right? Depending on your application. If you're a doctor and you have two genes that are important, you probably want to pick them all. But if you have an image and you want to compress it, maybe one is good enough. So it turns out that if you now combine the ridge regression and the lasso penalty, you can kind of interpolate between these two situations. If you put just a little bit of L2, you can convince yourself that immediately you are going to get all correlated variables, because now the functional is strongly convex. So it must have a unique solution. And if you have two variables that they're the same, the only way to get a unique solution is to put half weight on one and half weight on the other one. Because as soon as you do something different, you can do like this, or you can do like this, okay? So because you have two variables that are just equal, and so you can always put, say, 2/3 weight on one and 1/3 on the other, or the other way around, because they're the same thing, just with different names. So the only way to get a solution is to spread the weight equally on everybody. So this is a bit quick, and I'm going to repeat it, but in some sense, elastic net is a way to deal with correlation, and the way you deal with it is by selecting correlated variables. Elastic net is the name of this combination. And you can solve it exactly like you did before. All right, so let's stop here, and then we'll start again with the second part, which basically is gonna go from this simple sparsity for now, just been coefficients different from 0. We're gonna make much richer hypotheses than this and try to kind of exploit the same ideas. All right, so let's meet in half an hour.